our model, let's develop our model for light intensity. Or distance. So from the radius or from the distance from the light source. And we could say that that intensity, let's just call it I, or we'll just write it out, intensity. How do you think that should relate for what we know about the area and how strong the light bulb is? So one factor is the light bulb, what the light bulb is, how bright it is. So we could call that brightness. And how does that relate to that brightness, if you're really close, is all on one smaller surface area, and as it goes out, it's on a larger surface area. So it spreads out over the area. Okay. And the surface area is on the bottom because as the surface area gets bigger, the light intensity gets what? Smaller, right? So the brightness, what's a good measure of the brightness here for the bulbs? The wattage, right? And what was our surface area? Pi r squared. So it doesn't just relate to just distance from the light source. It relates to an inverse difference squared. And we see that come up a lot. And the reason it comes up is because it's spreading out in spheres around things. So we'll see the same relationship when we talk about the gravitational pull between different objects. We'll see that squared relationship come back. We'll see the squared relationship when we talk about the electrical charge between two charged particles. The distance, it ends up being an inverse distance squared relationship. So wattage over 4 pi r squared, okay? So let's say that, let's see an experiment here. We have a 100-watt bulb and a 40-watt bulb, right? So if I ask what the intensity is for the 100-watt bulb at, say, 1 meter from it, okay? So what is the intensity of, or for the 100-watt bulb at 1 meter? Well, we just calculate it, right? I equals 100 watts over 4 times pi times 1 meter squared. So our units are going to be watts per meter squared. I need some light. There it goes. I had to bring it closer, right, to increase the intensity of the light to get my calculator to come on. So 100 divided by parentheses 4 times pi times 1 squared. Only the 1 is squared. Of course, that's just 1. I'm having problems because of lack of light. Yours runs by batteries, so. .96 watts per meter squared. Let's see where we would have to put it for the 40-watt bulb. So now I'll turn off Oops, I turned off both. That's not what I wanted to do. Sorry. I wanted to pull the... For the 40 watt bulb, let's find what distance and then test it. We would get for to achieve that intensity of about 8. So what distance for the 40 watt bulb would have the same, or the radius, would have the same intensity? Okay, let's see. So I equals wattage over 4 pi r squared. Now we know the intensity is 7.96 watts per meter squared. We know the wattage is 40 watts, but we're looking for R. How would you go about solving that equation? Okay, so we could just cross multiply it in this case, right? Bring it up. So let's bring this up here. So we get 4 pi r squared times 7.996 times over meters, watts per meter squared equals 40 watts. Now what do I do? All right, so let's do that. Okay, for the number wise here, they just divide out, right? 40 divided by 7.9, oops, 6 is 5.03. Now for the units, I have watts over watts per meter squared. What does that give me? Just meter squared, because watts divided by watts per meter squared, you see how that's just watts over watts divided by meter squared? That's the same as watts times meter squared over watt. So those cancel, and you're left with meter squared. So now we have 4 pi r squared equals 5.03 meters squared. Now what do I do? Someone different. Tommy, what do I do? Yeah, or how about 4 pi? We'll make it a little easier. So 5.03 divided by 4 pi. Now I'm going to put that 4 pi in parentheses because I don't want it to, I want it to know that it's dividing by both. And that's a common mistake to make. 0.400. Oh, good. So that's working out nicely. 0.400 meters squared equals r squared. Oh, now how am I going to solve for that? Square root, right. So, oops, r will equal the square root of 0.4. Should be something easy, right? Nope, 0.63. Oh. that what you got? Seems odd. I would thought it worked out, but I guess it doesn't. Yeah. Okay, 0.63 meters. So for that same intensity, what do we need to be, for that same intensity for the 100 watt bulb, was at what? 1 meter. Now we need to be at an intensity of 0.63 meters, right? I was thinking to test it, but I messed it up because now I don't know how to test it exactly. Let's see. So let's see if we could just see if it looks like it's the same intensity. So if I take the, or I could move these so that I have 1.63 in between them. Like that, the 100 watt bulb. And then if I put this at 0.63 meters from this one, so 10, 20, and we turn on the other light, they should be about equal. We'll see how close we are. Well, we'll be off a little bit, but let's see how far off. Well, let's see. I mean, if I go... All right, now I have to move a little closer to that. So what are some factors that would affect this? Well, why would I be off? Or why would we be off? You help me, remember? Carolyn? Oh, I'm sorry. Courtney? Okay, so the wattage might not be exact, right? There's light coming from other places. What else? Okay, so light's bouncing off. It's not a perfect point, is it, inside that light bulb? It's a filament, right? So there's that. But we did all right with it. Now the distance to the sun is 93 million miles, right? So if we took this out on a nice sunny day and we found where the light bulb matched up to the sun, right? That distance. Then we could say we have this thing. We could find, we could set up the relationship of the intensity from the sun would be the same as the intensity from the light bulb, right? And we know the distance to the light bulb, so we could calculate the wattage of the sun. Because if we know in that relationship, the I's would be the same, right? And if we know the 100 watt and its difference, then we could set up, we could find 100 watts in distance, we could find I for the 100 watt. And then if it's the same I for the sun, we could calculate the wattage of the sun. But I don't think, well, it's, the hard part of that is setting up the light bulb and the situation to do it. But if we could do that if we needed to. All right. So that's just a little introduction in developing a model. And I talked some more about like planet models and things like that, and more about graphing and stuff like that in the video, okay? And so now, do you guys have your homework packets on you? Let's take a look at those. I have extras over there, but I thought I had one here too. Well, it's like the 23rd. Why not? When does it say the packets are due? It doesn't say yet. You just work on them as you can. Although I'll do a check on them at some point, but I'll tell you when that check is coming up. And I'll tell you what you should be through by then. So, upcoming, you see the early date for the packets is the 23rd. The due date is the 24th. Okay? The next thing you have coming up is to watch the video for really tomorrow. So tomorrow I'll check your notes for that. And then Friday you'll have another video to watch. And then next week you have the chapter block due. And the knot lab due. The knot lab we'll be working on starting tomorrow. But for that knot lab we'll also be doing a lot of it in class together. Okay? So as we will do a lot of the packet in class together. So let's look at let's look at page 4 of 14 on our homework packet. I don't know what I just did. Okay. So if we go to 4 of 14 here, I don't know how it will work on this. Why didn't it? That's not right. What do you have for your 4 of 14? Why is this different? Oh, I see. Okay. It's still 4 of 14, but it does it differently. Okay, so it gives you some data collected during an experiment. It says plot the data, find the slope and intercept in the best fit linear model. Okay, so a screenshot of that. Oops. Nope, no, that's not what I wanted. There we go. Okay. There it is. Okay. And it gives you a grid. So we have time versus length, don't we? And it wants us to find, now, okay, so which one's the independent variable and which one's the dependent variable? Okay, so Tommy wants to tell us. So independent is the time, and dependent is the length. Okay, it says that. Now, where do they go? Which one goes on the y and which one goes on the x? David? Jack, I mean, I'm sorry. Called you your brothers. That's right. So the independent variable on the x and the dependent variable, it's dependent on the time, goes on the y. So we'll label these axes first, length, meters, and time, seconds, right? Seconds, yes. Now what's our next step before we plot this data? Yes. A scale, that's right. Let's get some light going in here. One of the nice things about these rooms is I have the shades closed for that, but a good portion of our time we get to work in just natural light, right? And studies show that natural light is actually very beneficial to student performance. There's less fights and stuff, so Tommy and Jack are less likely to break into a fist fight. It might be, I think it might be Annika and Tommy though. So, anyways. So time goes from 0 to 16, and we have 1, 2, 3, 4, 5, 6, 7, 8 divisions. 16 divided by 8 is 2. So if we go by 2, we should be fine, right? Well, that worked out nice. Now the length goes from close to 0, 1, to 13. And we have 1, 2, 3, 4, 5, 6, 7, 8. 13 divided by 8 is, let's do 2's again, right? You see how that works? Because 13 divided by 8 would give us 1 point something. But if we do 2's, that would make much more sense than having our divisions be 1.3, right? Maybe. Or usually. So 2, 4, 6, 8, 10, 12, 14, 16. Now, okay. Now we'll make some points. What do we got? 1, 2, 3, 4, 5 points. Now you just come up and grab a point and plot it. Who wants to go first? Will? Okay. Do the first one. Well, I guess it doesn't matter. You can do whichever one you want. Okay, Will's grabbing the... Oh, my mistake. Sorry. I forgot to touch. Or I could just do infinite cloner on this one. There you go. Now just grab it and put it in the right place. So he's plotting up, let's see, it looks like 4. He did 0, 1.1. Okay, who's next? Okay, Gracie? Who's after Gracie? Okay, go Tommy. Who's after Tommy? Gotta be, okay, go Courtney. You can get right up after him. And then Jack, you want to do it? Go for it. You'd need your rulers out, so you might want to get those. Anyone not have a ruler? A couple people. You just need the straight edge. Why is one off the page? Oh. All right, we'll fix it. Who needed one? Oh, we have to fix it, so hold on for a second. We have to undo some work here. What the heck, Jack? All right, so we have 16, 12.8, 4, 3.2, 0, so 8, 7.4. And we have 12, 9.2. Like that. Okay, now we can fit our model, or fit our line first. So take your ruler. Now, your data might be slightly different than mine. But see, I'm going to fit my line like this. Go ahead, draw yours on yours. And then tell me, okay, what's the key part of this? We have to pick points where? Sam? On the line, right? Because if we pick like these 2 points, that's not good data, right? That's not going to fit our data well. So we pick 2 points on the line. So go ahead and pick 2 points on your line. Go ahead and find the slope. Go ahead and find the y-intercept. And then write the mathematical model, okay, to it. If you have trouble, you can ask me for help. What's that? Yeah, find the equation of the line and the intercept. Looks good. Anyone having trouble? Raise your hand. All right, good. So you can keep working, but so they probably vary a bit. So what did, and there's some of you still working, that's okay. What did you get, Kelly? For the slope? 11.1 over 6. What was your, all right, but remember we picked points on the line. Okay, good. So, right, so you picked these two because they were right on the line. That's all right, but the best thing to do is to, but it seems like maybe you're off. Like you did it backwards. Did you do x over y? Did you do y over x? What did I get? Yours is too high, though. Let's see. Maybe you counted boxes. Okay, so if I pick this point here, it's a little lower than on mine than that one. And this one here, that's about 16, 12.5, I'll say. Now yours might be slightly different. That's okay. And that one's about 0, 1. So the slope m is change. Now this delta we see a lot in physics. That's why I'm putting it here. And it means change. y2 minus y1 over x2 minus x1. The y2 is, it's what for me? Monica? 12.5 minus, okay, so this is the y2 because this is the xy point. Now, it wouldn't matter if you did 1 minus, as long as you're consistent about which is the 2 point and which is the 1 point. Okay? So 12.5 minus 1 over 16 minus 0. That gives us 11.5 over 16. What did you have? Oh, 16 you said, though. Oh, that's why I was confused. Yeah. Okay, so 11.5 divided by 16 is 0.72. Now, if you're still confused how to do that, that's okay, but you should probably come see me for help with the packet problems on that so I can help you. But there's more to it that probably a lot of you left off. What do we need with this? Did anyone put their what on there? We need the y-intercept as well, but I was thinking more for just this one. Units. What are my units on the y and my units on the x? Y units, so it's meters, right? Over, what does that remind you of, meters over seconds? A speed, or miles per hour, right? So that's telling you the slope on a length versus time graph is the speed. So we could develop a mathematical model between length versus time and come up with the speed, okay? So we could have Hannah, right, run around the campus, and we could record her time from start and the distance she's gone. And we could plot that up, and then we could find the slope of that graph of hers, if she's running at a consistent speed, and we could calculate her speed. Okay. And then, all right, so let's see. What else do we need to do here? Oh, y-intercept, right? What's our y-intercept? About 1, right? Maybe 1.1 if you can read it on there. I think I had, well, whatever. So 1, and what are the units on that? Meters. Just meters. Just the y. So when we look at our model now, it looks like this. Y equals 0.72 meters per second times x plus 1 meter. Okay? Except we probably shouldn't use y and x, right? We could put in there length and time. So we'll just use L. T for time. I'm going to give you different things other than L later, but right now that's what it is. So if you plug in a time, say 2 seconds, what are you going to get out? Kyle? We'll get the length in meters because the seconds will cancel and we'll get length out. So here's a nice mathematical. Now if you had 0.75 or 0.78 and this was 0.8 or 1.2 or something like that, is that wrong? No, because we're estimating it. If we put it into Excel or some other program that will do statistics, like our little green thing over there, we'll be working with those and getting lines and stuff. That will give us a slope based on a statistical slope on it. Now, Annika has a chance of being in statistics. Are you in statistics? Okay, you are. So you'll learn about some of the difference of the squares summed to calculate. So what it's doing is it's taking each point on this line statistically, and it's looking at the distance from the line there, and it's squaring that distance, and it wants to minimize that value of the distance So it gets the best line that minimizes that value. And you can do this mathematically, and it will take you pages of, that's, they made me do it when I was in school. It takes you pages of paper. But now in like Excel, you just go, what's the best fit line? It gives you the slope in a second, right? Or less. Okay, so there's one for you. Good. Now, when you watch the video, you'll also learn about fundamental quantities and derived quantities. Okay? So, this is nice when you guys like come to class early. It gives us more time. So, I appreciate that. Thank you. Anyways, fundamental quantities. Fundamental quantities are just measurements of, or things that we look at to measure for, to get specific, like the length of something, the time of something, like that. Is that where this is? And so the three that we'll look at is mass, the mass of something, and the units that are associated with that mass are kilograms in physics. Now when you go into chemistry, your fundamental quantity for mass will have the units of grams. But for us, we use kilograms because we're talking more about everyday objects, okay? Especially for classical physics, right? And the other one is length, and that's in meters. And in chemistry, you'll have centimeters usually. And then the last one is time, and that's seconds, and it's just S. Okay. Now, everything else that we have in physics derives from this. So everything else becomes derived quantities from our fundamental quantities. So if we had something like speed, what is speed? Well, speed is length over time, isn't it? Just like we just saw. That's a derived quantity, meters per second, right? So that's all that is. Density. Well, density is mass over volume, right? But volume is just a length times a length times a length. So kilograms per meters cubed. You see? All right. Now you could play with derived quantity stuff. I think this class ends at 25 after. Is that right? Okay, so we won't do any more right now. Tomorrow we'll start the lab, but you should basically be able to go through and do all your 1.1 problems in the packet. Okay. Oh, but in practice problems, let me show you something. Let me go back to here. There's one somewhere. All right, so this should be 345. If it's not 345 on yours, fix it. It is, I guess. The last page. Because some of them I printed out wrong. But it should say 345. Do you see? Some of them might be different like yours. Okay, fix that. And then this should be 3 centimeters, but it's corresponding to this. You probably don't have that line in there for the radius. It's a 3 centimeter radius. Because you can't really do the problems without that. So, okay? So fix those. Keep working on these packets as we go. Okay? Once we cover 3.2, we'll have a check on how far you've gotten with those. Okay? Now there's some trig stuff in there. If you know that, you can go ahead and do that. If you don't worry because we'll get to it.